Thank you very much. Hello. For those of you who do not know me, I am Miriam May, and I'm the CEO of the Friends of the Arava Institute, and located in scenic and a little bit cool Newton, Mass. We're delighted to have you here for this mini class in our series of informative and relative programs. We've gone from dates in the Earth and all sorts of things. Now we're going sky high or space high, shall we say. I am delighted today to welcome Shimrit Maman, who is the Research Associate and Director of the Earth and Planetary Image Facility at Ben-Gurion University of the Negev, with whom we partner on accreditation for our student programming and in many other ways. We are welcome to have friends and supporters of the Arava Institute, those who support us and colleagues from the Jewish National Fund and from our online universe, including alumni and other interested guests and a variety of board members who are joining us today. We're delighted to see you. Dr. Shimrit Maman is the director of the Earth and Planetary Image Facility at Ben-Gurion, and her research deals with the application of satellite technologies, remote sensing, and GIS, and she'll tell us what all those things mean, to environmental challenges and climate change. She's an integral part of the research team leading BGU SAT. That's not an exam you take to get to college. It's Israel's first research nano-satellite. She also leads diverse education and outreach programs, one of which I find really compelling, the unique all-girl international remote sensing science program called Space. She also has served as a UN Spider expert at the board, as the board director of DMARS, and as a founding board member of Space, a women's association promoting gender equality among science, technology, engineering, arts, and mathematics professionals. She also teaches a course called Climate Change for the students at the Arava Institute. Welcome, Shimrit, and we look forward to learning from you. Oh, and if you have questions along the way, just put them in the chat. I will either call on you or ask.
Okay, great. Thank you so much for having me. This is a great opportunity. And I will just start with the presentation as I don't have a lot of time. So as I was introduced, could you see the presentation? Is everything working well? So,
Shimrit, can you get slightly closer to your microphone? Shimrit, excuse me, can you get slightly closer to your microphone, please? Thank you.
Okay, is this better?
Yes.
Great. So as I was introduced, I work with satellite data and more specifically with climate change research that combines satellite data. So I'm just going to show you how it's done. And it says nano-satellites, so I'm going to discuss that briefly as well. So basically, we have what we know as Earth observation. And this is already something we know and is established for 60 years now. Most of you might know it by the name of remote sensing. Basically, it's the acquisition of information without coming into physical contact with it. So this is something we already have this is a picture, for example, from 1960. So for over 60 years of Earth observation. So what's new in this field? That's the main talk today. So what we're experiencing in the past years is actually we're seeing how these spacecraft are becoming smaller and smaller. And I put here some example of satellites that are mainly in use and their weight. So you can see here an European satellite, Canadian and European, which is called NVSat, and it weighs 8,000 kilograms. And look at the people here just for scale. In the years, we could see the satellites getting smaller and smaller, and their weight is reduced. And it gets so small that we're talking about microsatellites that weigh already between 50 and 70 kilograms. But what I want to show you today is even smaller. So I have an example here, which is a nano-satellite. I can't show you the real thing because my nano-satellite is up in space for the past 3 years. But I am going to show it to you as a demo, but this is how small our satellite is, okay? This is an exact replica. It's a bit bigger because I'm just going to open its solar panels now, so it's going to look a bit bigger. But still, this is the exact size, and this is how it looks in space. Okay, so it's a bit bigger when it's open, see, but this is the size of the satellite. So that's the size of a nano-satellite. What we see in the past years is between 2014 and 2018 that most of the satellite missions, and especially in this category of nano and micro satellites, are for Earth observation or remote sensing purposes. Now, this is quite biased because in 2017, I'm going to show you that movie in a second, but we had one specific launch with 103 nano-satellites. So that number increased this percentage greatly. But as we look at future missions, we still see that most of the satellite missions are designed as Earth observation and remote sensing in this category. So we understand that this is something that is becoming very popular and very widely used. And the main reason for that is the reduction in launch I'm sorry, I lost my words. The reduction in weight allows us to launch more because the weight is the most limiting factor in the launch process. So Ben-Gurion University went into this project of nano-satellite with a couple of objectives in mind. The first one was a technological one. We wanted to show a capability demonstration. We wanted to show that actually we could perform the same work that a large satellite does using a nano-satellite. The second objective was to allow our students to educate with real hands-on experience. It's just like teaching someone how to swim without a pool. And we wanted to allow our engineers and all our students hands-on education and projects that are satellite related and space related in all kinds of fields. This nano-satellite, it seems like our lab is in charge of, but we have over 30 research groups from different fields. It's very multidisciplinary, and it crosses a lot of different disciplines, even on the psychological level of how you reach this mission. I have to admit that our third objective, and it came in third, was a scientific one, because we were so busy. First of all, you enter this project with so many high expectations, and you get caught up very fast with the engineering that you forget sometimes that we could produce much more. And because of all the problems that come along the way, it took us a while to understand the full potential of the scientific mission, as I could state now 3 years into the launch. So this is the real thing just before I was launched, and you could see it in you can see the size by looking at the picture. That's why I show the replica. But this is a 3U satellite. Okay, a 3U CubeSat means that it's made of 10 centimeters by 10 centimeters by 10 centimeters. Okay, and we have 3 units here. So these units together are 10 by 10 by 30 centimeters. That's the dimensions of the satellite. This is a low Earth orbit. Currently, it's at a height of 500 kilometers above ground. And the most unique thing about this satellite is that it has a shortwave infrared imaging system on it. And currently, this is the only nano-satellite in space with such a camera. This is a joint project of Ben-Gurion University along with the Israeli Aerospace Industries and the Israeli Space Agency. So on February 15, 2017, the satellite was launched, and it was launched on the Polar Satellite Launch Vehicle from India. I'm not sure I have the time to show you the video, so I'm just quickly going to show you parts of it. Just a moment, I'm just moving to a different screen. And I'm skipping the music so I could speak on while it's running. Could you see it? Is my screen? Yeah, okay, great. Yep. Okay, great, thank you. It's a bit hard to not know if you're with me or not. So, so okay, so the side camera is also available, which gives us a really unique perspective of the launch. And I'm just going to skip to the part where all the different parts of the rocket are separated, okay? And here, this is the third part of the rocket. And now you could see the main reason. This is the Cartosat, this is the Indian rocket, and two more nano-satellites here and here that were launched with it. Now this is Earth.
So Shimrit, can I throw in a question?
Yes, of
Do
course.
all the thousands of satellites launched by companies like SpaceX, et cetera, interfere with the Earth observation satellites? That's a question.
But every satellite is launched into a unique orbit, and every object in space that is larger than 1 centimeter is tracked by NOAA, and we have the ability to see exactly where each object is. We do have a problem with that is called space junk. And this is something that we're dealing with as a research topic, but as a serious problem in space, because we have a lot of satellites.
We need a space vacuum cleaner. Maybe
exactly.
The pace.
Exactly. So what's unique about this launch is that it had over 104 satellites in one launch. So you could see here, every 6 seconds, a nano-satellite that is being thrown. And this was applied from two parts of the rocket. And I'm just going to skip, and you see this cloud of satellites being thrown into space. And the most amazing thing about this launch is that all satellites were operatable, which this is something that is very unique in space terminology. So I'm just going to go back to my presentation. And you could Google this video on YouTube if you would like. Just coming back to my presentation. Thank you.
Maybe we can put up the link at the end.
Okay, great. Absolutely. So that was very exciting. It's really exciting to see it afterwards because during the launch, that was at 5 in the morning, we didn't see anything. We just got a screen after 10 minutes saying all satellites are in orbit. And then we started our race to communicate with our satellite. So in order to communicate with our satellite, we had to build this ground receiving station, which is situated on the roof of the lab. It's a 6-story building, so it's very high. And then we started tracking the different satellites. The thing is for 2 weeks, we had no communication. It turns out that we were tracking a different satellite. Now we have a really small window of 15 minutes each time to communicate with it, and the tracking antenna is moving as well. After 3 long weeks, we finally got our signal, and this is how it sounded. So Some of you might remember this. This reminds of the fax machine that used to be. We get this signal and then we translate it into telemetry, and we communicate with the satellite that way. So we could actually tell the satellite where we wanted to shoot pictures for us. And when we did that, we received that we tell the satellite where we want the images to be taken. And we already have more than 6,000 images of Earth. And these are some of the location we took images in that we could analyze and use for our research. Now, comparing it into large-scale satellites, currently, well, this is currently to 2018, but the numbers haven't changed much. Some of the number of satellites in orbit now that are operational, something around 5,000. The ones that are active, and I'm talking about Earth observation satellites, are something around 2,000 satellites. But if we deduce that, and we want to see how many of these satellites have a shortwave infrared sensor on them, we actually see that we have only 11 satellites with active shortwave infrared sensors on them. And if we take all the nanosatellites that we have currently, about 2,050 nanosatellites in space that are active, we see that we only have one. And this is BGUSat, this is our nanosatellite. So these are some images of the satellite. In the left, you could see, in the left image, you could see the satellite passing over Israel. And because I'm showing you the shortwave infrared imager on it, it has a single band, and the satellite passes really fast. At a height of 500 kilometers, it travels in the speed of 7.5 kilometers per second. That means it rotates Earth every 90 minutes. It is really quick. So we could communicate with the satellite between 2 to 4 times, depending on the angle we see it at that specific day and the orbit that it crosses. And we have about 10 to 15 minutes to upload the data and download the data. On the right, you could see, again, Israel, but this GIF is separated into two because on one, Israel is clear and you could see the coastline really nice and you could see some clouds as well. But on the left, you could see how Israel looks when it's all cloud covered. Now, what you could see amazing on this right animation is that our satellite is also able to move. We actually have an attitude control that we could operate from the command. So that's really unique using such a small satellite. So when we talk about climate change and what we could do with such a satellite, then we have several issues we deal. So first of all, meteorological research is obvious from the cloud cover I'm showing you right now. So cloud coverage and storm observation are a basic thing using shortwave infrared sensors. But we also try to allocate CO2 concentrations because this specific band has absorption peaks of CO2. Also, we could see different things like differentiation of clouds from snow, which from the visible point of view is really hard to tell. If you're looking just from the visible part of the spectrum, it's really hard to see it because you see them both white. But snow and clouds have a unique, different spectral signatures using this wavelength. Also, we could tell apart from soil moisture and one specific research I'm going to show at the end is the Earth air glow. So just to bring you back to the objectives of this study, one of the things we said that is we want to show a technological demonstration. So we have here two images, remote sensing images of two different satellites. One is called BGUSat, which is Ben-Gurion University satellite. That's what I just showed you. And the other one is NOAA. Okay, this is an American meteorological satellite. Now, obviously, this is a question, but nobody talks to me now. But I usually ask my audience which result here is of BGUSat. And BGUSat is actually this image. Now, the most amazing thing about this is that this image taken from NOAA is this size of a satellite. And you could see here the people for just to scale the satellite. So we actually showed that we could get a better resolution, a special resolution. You see better results from a much smaller satellite. Comparing it to different satellites that are now operational and acquire data, we could see that most of the satellites that we could compare it to have a revisit time of 1 day. Okay, and our satellites could come in every day, but if we want to enhance our spatial resolution, we are actually, if we go here, we're actually getting better spatial resolution, but the revisit time drops to every 2 weeks. So there's some kind of a trade-off. One of the things we want to show is that using nano-satellites, especially in constellation mode, could enable us to enhance our spatial resolution along with our temporal resolution and get much higher results than we get from the really large satellites. And that's just what I said now. So if you want to play with the data for any reason, our data is available for free because you just type in Google BGUSat image browser. We do ask you to register because we do want to see who uses the data and see if we could collaborate and learn from each other's research. The data, I said we already have over 6,000 images available. Not everything is on the browser now because it takes time to upload the data. Once we get it, we have to work on it and improve the data for research analysis, but we also put the raw data in as well. And you could download it and make whatever kind of research you want with it. Ongoing research right now with the satellite is in our lab. Is first of all, together with Tel Aviv University's Professor Colin Price, is a comparison of the existing satellites to Earth globe. Earth globe is this layer that you see here. This picture was taken from the International Space Station. And the thing is that we have some excitation of oxygen molecules in this layer that show us this unique phenomenon. And this layer is just too high for airplanes and too low for satellites. So coming closer with our satellites to a low Earth orbit with this specific wavelength allows us.
I'm saying to put people's.
I'm sorry. Allows us to study this layer better. And another thing that we're currently working on is, and these images are taken from the Arava, is change detection between two dates of the same bodies, especially the large one, because we have a 600 meter resolution per pixel. And we want to see the flash floods, how they influence and how we could see the difference in reflectance in these arid and non-reachable environments. So this is the mission patch, and it explains most of the things about the satellite. You could see Ben-Gurion's head, and every satellite mission has its own patch, so we had to do ours as well. So this is Ben-Gurion University satellite. These are our associates. And we actually wanted to show that this satellite is looking to the Middle East with scientific purposes that influence the whole, not just the region, but the whole globe, because climate change is something that is not site specific. This is something that everyone is affected by. And this is the atmosphere and the main objectives of the research that BGUSat deals with. So I was introduced also as a United Nations mentor for gender equity. And one of the projects we are working using nano-satellites such as BGUSat and microsatellites such as Venus is allowing girls in our lab. And it's not that we do not allow boys in our lab, but the thing is that we saw that we have a real problem keeping girls in these fields and interested in this in space sciences in particular. And by doing that and allowing them to experience hands-on with the with the data and operating the ground receiving stations, we achieve United Nations Sustainable Development Goals number 4, 5, 13, and 17, because this project, She Space, has already left the boundaries of Israel last year, and we already collaborated with Brazil, United States, Germany, and Israel, working all together in an international project. And these girls, this is the Israeli girls on the right and the German girls that are not dressed up. It turns out we flew our girls to Germany to an all-girl conference in the Oktoberfest. So we got the whole of the German experience, and together these girls promote not only space sciences, but climate action, and they act as little ambassadors for women in space sciences. So if you have any questions, I would like to,
So I'm gonna
answer them now.
flag a couple of questions for you, Shimrit.
Okay.
One question is, this was launched with India, we heard, and
Yes.
India isn't always Israel's best friend. How was that arranged, and what other countries were involved in that launch? And that question comes from Joel Kramer.
Okay, so most of the countries that, well, first of all, the reason that it was launched from India is it was just the closest launch available. Because it's a small satellite, and if you remember while I was showing the movie, I said this is the Cartosat. The main payload on that launch was the big satellite, and then everybody else on that launch was just like a piggyback ride. We just flew in using this giant rocket taxi because there was room. We just squeezed in.
Do you have to pay for your cab? Is it
Yes,
Uber, or is, you know?
Yes, the launch costs around $200,000.
Wow.
Yeah. But that's really cheap in space terms.
Okay. Alex Bernstein asks, how does this satellite compare to Planet Lab satellites? How many are in space? What's the resolution? How many Earth passes per day?
Okay, so most of the satellites that you saw in the video, 80 of them, I said this was a historic launch, 104 satellites, 80 of them belong to Planet Labs. That's why the large number as well of Earth observations that on the slide I showed. The Planet Labs, they're not called Planet Labs anymore, they're called Planet. They're a bit, the doves, their satellites are called doves. They're a bit smaller. It's a 2U satellite. That means it's this much smaller. Okay, so it's just this part. It's a 10 by 10 by 20 centimeters. And the thing is that they don't have a shortwave infrared sensor on them. They have an RGB and near infrared camera. So that's different parts of the electromagnetic spectrum. But they have a fabulous spatial resolution of 5 meters.
So does this Do these satellites help you measure um, things around the water? You know, how much water is that? I know you noticed, you talked about the wadis and the rain, the effect of the flash floods, which I know has cost lives. We're actually, some of us who are on this call were at Keturah when those young people were tragically killed in a flash flood. We were just coming from Petra when all traffic stopped in the Arava because of that tragic thing. Does this help us predict when these things are going to happen in the future, and we'll be able to be smarter?
Well, it could help us predict if we take the meteorological data in advance with the satellite movement and the cloud movement. This is how we actually monitor things like hurricanes, okay? But usually flash floods are on a much smaller scale, and we don't use them to predict, and we don't use the satellites to predict, but we use the satellites now to analyze the properties that were influenced, the characteristics of the body of the river that was influenced by the flash flood. And there are groups that work with modeling and prediction. My group does not do that.
Mm-hmm. Great. You want to tell us a tiny bit? I don't know if we have 2 seconds for you to tell us a little bit about your course at the Arava Institute about teaching climate change.
Yeah, absolutely. So I'm actually teaching 2 courses this year. The first one is climate and change, because it's not just about climate change. I believe that you have to understand climate in order to understand the change. And that's why I give a bit more of a physical context to the course. So we first start with what is climate and what's the climate on Earth, and then we understand the change. And the second course I'm going to give in the spring semester is environmental remote sensing. So that deals with all the satellite technology and how we use it to monitor Earth in different environmental aspects.
Great. Thank you. Other questions? Deborah, you asked about Earth ecology versus space ecology. I don't understand the question, but maybe Shimrit does. Or do you want to unmute and ask yourself? That's possible.
Well, yeah, there are so many satellites, especially SpaceX is only the beginning. We're going to be what is metaphorically a Dyson sphere surrounded by satellites and not being able to see the sky. And so many of these also turn into space junk. They're not junk when they're working, I assume, but they are obstacles to vision of the stars for astronomers, not just romantics. So this, I mean, these are tiny, but they're contributing to what encircles us. So that's what I mean by ecology. And what do you respond to that?
Okay, so this is a great problem, and I'm sharing the screen now. And this is an issue that is targeted by a body that is called United Nations Office for Outer Space Affairs, UNOSA. So actually now there's a lot of regulations about each launch. You can't do what you want in space because we understand that this is how our space looks now. So there are regulations and there are legal ways to deal with it. And there's also startup companies that are now developing it with the purpose to clean space. There's actually an Israeli company that is called Festive Space. And what it does is, especially in the really high satellites, the satellites that are at a height of 36,000 kilometers, according to regulations, once the satellite stops operating, you have to leave a bit of fuel in order to take it out of the orbit So it goes into a place called a satellite graveyard. And the thing is, some of these are stuck because if they could lose command or something can go wrong. So one of the things that this company is offering is a service of a small satellite that actually comes to the large satellite and just pushes it out of the orbit in order to evacuate this space. But it doesn't solve the problem of junk. It just pushes it away more from Earth.
Thank you so much, Shimrit. I'm going to, Rachel Durning is going to share in the chat information about our next session. We have some regulars here who are always joining us to learn. I think this is a great example of the level and the quality of the teaching and the studies that take place at the Arava Institute that our students are exposed to. We're going to, our semester will start late because first of all, getting people onto campus was complicated. And now the shutdown in Israel for 3 weeks over the holidays would have led us to open the day after the shutdown, which made it impossible to get people in. We're having issues, the Jordanians aren't opening their borders, so we're not getting Jordanian students. We've had some issues getting American students because of visa issues. So it's going to be a smaller cohort this fall, but we are hopeful that all these issues will be resolved and we'll all be healthy and well, and Israel will have brought its daily load back down. It was 20 and now it's 5,000 in a most reasonable way. And we'll be able to also get visas for our American students in a normal way, et cetera, and so forth. So, but nonetheless, the semester will go on and Shimrit will be one of the faculty offering classes. Rachel Durning is going to share information and has. Our next session is Wednesday, September 23rd, and it's Dr. Clive Lipshin, who many of you know. He is the head of our water programming at the Arava Institute, and he will be speaking on the COVID-19 wastewater sampling that they are doing in Bedouin and other communities as a way of detecting COVID-19 before it's symptomatic in these communities and therefore able to get the health and safety measures in place. This is jointly funded by the Jewish National Fund, and other institutions that brought us the funds to make sure this project could go on, and really is a example of us not only learning the work, but being able to deliver into our shared society. So thank you very much. I wish you all who so celebrate. First of all, I want to thank Shimrit. I want to thank Rachel and Elisa for making this happen. And I want to also thank you all for joining us and wish those of you who celebrate a Shana Tova. And may it be a sweeter, better, easier new year of health and calm and being able to be with each other. And God knows I'm looking forward to hugging regular humans beyond the ones in this house. Thank you so much for being with us. And if you have any questions, we're gonna, Shimrit, is it okay if we post your address as well so that we can, people have questions, they can follow up with you or with us, and we'll make sure we get answers. Thank you all. Shana Tova.